Okay, so I thought I would make some comments on the extra homework that was due last week. Now, of course, there's always more than one way to do the problem. For some of these, I'll show multiple ways. You might have done the problem a different way, and I welcome discussion. If you're not sure the way that you did was valid, or if you have some questions about the ways that I show, please get in touch with me. Be glad to talk to you about your ideas. All right, so let's go ahead and start with this, make it a little bit bigger. Okay, and we can make this big. All right. All right, now a matrix P is called a projection matrix if P squared equals P. If you do P twice, it's the same thing as doing P once. Okay? We saw in class P zeroes out certain directions and preserves certain directions. So some vectors get smushed down to zero, and some vectors get preserved as you keep hitting them with P and nothing happens to them. So in the following exercises, we're always assuming that P squared equals P. All right? So number one, show that every vector in the column space of P is an eigenvector of P with eigenvalue 1. Okay, there are two ways to do this. You could take this equation P squared equals P column by column. If you remember, when you multiply two matrices together, that's the same thing as multiplying the first matrix times every column of the second matrix. What does that mean then? That means P times any column of P is that same column of P. So every column of P is an eigenvector of P with eigenvalue 1. Since every column is an eigenvector with eigenvalue 1, that means the entire column space consists of eigenvectors with eigenvalue 1. Number two, another way of doing it is if V is in the column space of P, that means that V is equal to Px for some vector x. Okay. All right. Now just evaluate PV then. What about PV? Well, PV is P times Px. So let's just write that out. And what's that equal to? Well, that's P squared x, right? And that's equal to Px, which is equal to V. Okay. All right. So I'm just giving this, I'm giving kind of a sketchy write-up. You could write a few more details, but this is the general idea. Right, number two, show that every vector in the null space of P is an eigenvector of P with eigenvalue 0. This is true for any matrix. For any matrix, the vector in the null space is an eigenvector with eigenvalue 0. That's the definition of eigenvector, right? So it's just saying Px is equal to 0x. So that holds. Number three, show that if P is of size n by n, then P has n linearly independent eigenvectors. All right. So far we've seen eigenvectors with eigenvalue 1, and then we've seen eigenvectors with eigenvalue 0. Every vector in the column space has eigenvalue 1. Every vector in the null space has eigenvalue 0. Now if you just add up the dimensions of null space plus column space, you get n. Remember how that works. The dimension of the null space plus the dimension of the row space is n, but the dimension of the row space is equal to the dimension of the column space. Okay. All right, so the two dimensions add to n, but you need to show further that these two different subspaces only intersect in the 0 vector. And this follows because they both contain eigenvectors with distinct eigenvalues. There's no vector in the column space that could be in the null space, because if it's in the column space, it has eigenvalue 1. So it cannot be an eigenvector with eigenvalue 0. And conversely, every vector in the null space is an eigenvector with eigenvalue 0, cannot be in the column space. So these two spaces are disjoint except for 0. Their dimensions add to the dimension of the total space. So every vector in P. So we have n linearly independent eigenvectors. All right, number 4. I unassigned number 4, but I can say something about it. In fact, whenever you have a subspace, or you have a basis of that subspace, you can always find an orthogonal basis with the same span. So you have the null space, which is eigenvectors with eigenvalue 0, and you have the column space, which is eigenvectors with eigenvalue 1. For each of those two spaces, you can find an orthogonal basis. So I have an orthogonal basis for the column space. I have an orthogonal basis for the null space. So all I have to show is that these two different bases are orthogonal as well. And what I didn't include in the original problem was to assume that P is symmetric. If P is symmetric, then eigenvectors with different eigenvalues are orthogonal. So we could get that all of the vectors are orthogonal. The vectors in the column space are orthogonal, the vectors in the null space are orthogonal, and the vectors between the two spaces are orthogonal to each other, which follows when the matrix is symmetric. But I disincluded the problem because I didn't say that P had to be symmetric. So this is only true if P is symmetric. So this is important. In fact, if P is not symmetric, it's not true. All right. So let's move on to 5. Show that a symmetric matrix P is a projection if and only if A, 1 is the only non-zero eigenvector of P, and B, P is diagonalizable with an orthogonal matrix, i.e. P can be written as P, D, Q, Q, D, Q transpose, where D is a diagonal matrix and Q is an orthogonal matrix. I.e. the transpose of Q is Q inverse. All right. That's what orthogonal means. All right. So let's take account here. All right, this is an if and only if problem. That means we have to show two different things. That means we need to show that P is a projection implies A and B, and A and B implies P is a projection. All right. Now, P is a projection implies A is B. That's really the only if part. So that means this clause implies this clause means only if. That will happen only if the result is true. Okay. It's a little bit confusing that if means the reverse implication and only if means the forward implication. If you think about it, that's how it works. Okay, so first let's prove the only if, and the only if part means that the projection implies A and B. P is a projection implies conditions A and B. All right, so what about condition A? All right, 1 is the only non-zero eigenvalue of P. Well, we saw that from part 3 above. What does part 3 above say? Part 3 above says, is it going to let me go there? Okay. Here we have P has n linearly independent eigenvectors. Some of them have eigenvalue 0, which is the null space, and some of them have eigenvalue 1, which was the column space. So we showed that the only non-zero eigenvectors were vectors in the column space which had eigenvalue 1. Okay. So that means that A follows from the fact that P is a projection. Okay. Part B, that's just a general property of symmetric matrices. Okay. So if I have a symmetric matrix which is a projection, then I will have both A from the fact that it's a projection and B from the fact that it's symmetric. Let's see if we can go backwards. The if part means that if I have conditions A and B, then it is a projection. So it implies P is a projection. Okay. All right, so let's suppose we have A and B. Well, in particular, we have B. So I can write P as Q dQ transpose. So let's look at P squared and see if P squared is equal to P. All right. So P squared is Q dQ transpose times Q dQ transpose. All right. Now, of course, Q transpose Q is going to cancel, and I get Q d squared Q transpose. Now, what do we know about d squared? Well, part A says that 1 is the only non-zero eigenvalue of P. That means that D must have 1s and 0s on the diagonal. All right. Any matrix that has only 1s and 0s on the diagonal and is a diagonal matrix must satisfy d squared equals d. You can convince yourself of that by writing some of these matrices and seeing that whenever you do multiply any two matrices with those conditions, the square is always the same matrix. All right. All right. So that gives us that P squared equals P, and that gives us that P is a projection. All right, next part. For any n by n matrix A and any vector v in Rn, we may write v equals AV plus I minus A times V. So that I minus A is a projection if and only if A is a projection. So this is kind of a decomposition. of V into two different parts. All right. So first of all, I want to show that if A is a projection, in other words, A squared equals A, then I minus A is a projection, so I minus A squared equals I minus A. Now you can just verify by writing down I minus A squared and then using the fact that A squared equals A to prove that I minus A squared equals I minus A. Right? So that means that A is a projection implies I minus A is a projection. For the only if part, you can be fancy and write A as I minus A. Okay? So if I minus A is a projection, then I minus A is a projection, but that means that A is also a projection. So that gets you both ways. Right? Same argument gets you both ways. Down to 7. 7. If the symmetric matrix is a projection, so the column space of P is orthogonal to the column space of I minus P. This is why projections with symmetric matrices are sometimes called orthogonal projections. All right, so what's going on here? Well, first of all, what are the implications of 7 on 6? If the column space of P is orthogonal to the column space of I minus P, then these two vectors here are perpendicular. They're orthogonal. So I've decomposed V into two orthogonal parts. That's a big deal because that means that usually I can use it to look at the two orthogonal parts separately. Okay, so it's like taking components of a three-dimensional vector. That's what you're actually doing. If you're taking the vector 5, 4, 9, and you're taking the components 5 along the x-axis, 4 along the y-axis, 9 along the z-axis, you're taking orthogonal components of that vector. So those are all orthogonal projections. In that case, there are 3 orthogonal projections. Here I only have 2 orthogonal projections. But you can see that you can build up a vector from its orthogonal projections. All right? And it's kind of a simple way of expressing the vector. All right? So we want to show that if you have a symmetric matrix P, then the column space of P is orthogonal to the column space of I minus P. In other words, these two are perpendicular. Okay. Now you can verify that directly. Remember, if something is in the column space of I minus P, it can be written as I minus P times X. If something is in the column space of P, then it can be written as Py. If you can just write down I minus P times X, inner product with Py, in matrix language we can write that as I minus Px transpose times Py. Right? And you can just work out using the fact that P is a projection and P is symmetric, you can work out that this is equal to 0. So that's one way of doing it. Another way is kind of to use a subspace argument. X is in the column space of I minus P. So if and only if I minus Px equals X. Now why is that? Well, I minus P is a projection. So the column space of I minus P is the set of eigenvectors of I minus P with eigenvalue 1. So any vector in the column space of P is an eigenvector of I minus P with eigenvalue 1. But you can rewrite this as saying that Px is equal to 0. The x's cancel on both sides. All right. And this is a if and only if, so the column space of I minus P is identical to the null space of P. But the null space of P is the null space of P transpose because P is symmetric. Okay. And the null space of P transpose is always orthogonal to the column space of P. That's true for any matrix. All right. So we've got this fact here. And so that gives us that the column space of I minus P is orthogonal to the column space of P. All right, two different ways. Of course, the first way is more direct. The second way kind of takes you through and shows you relationship between subspaces. All right, part 8. A rank 1 matrix A can always be written as A equals W times V transpose. This W is a column vector, V transpose is a row vector. If A represents a one-dimensional orthogonal projection, then what can be said about V and W? What is the geometrical significance of these vectors? Okay, so here I say one-dimensional or rank 1 is the same thing. One-dimensional just means the column space has one dimension. Right? So what are the geometrical significance of these two vectors? All right. Well, I think you know that the column space of A is going to be W. Because if I multiply A by anything, the result is going to be some multiple of W. All right, just put another vector here, x. W times V transpose X. V transpose X is a number, so the result is going to be W times a number. Okay, so the column space of A is equal to W. All right, now, so we know that W is in the column space, so W is orthogonal to the column space of I minus P. And we showed up here that the column space of I minus P is equal to the null space of P. So W, the column space, is orthogonal to the null space of P. Okay, I should say A. So here I should say, all of these should be A, sorry. So let's make that. Column space of A is orthogonal to the column space of I minus A, which is equal to the null space of A. Right. Now, what is the null space of A? Well, something's in the null space if I take some vector x is going to be the null space if V transpose x is equal to 0. In other words, if V is orthogonal to x, then x is in the null space. Right, that's what I said here. The column space is spanned by W, as we said, and the null space contains all vectors perpendicular to V. Okay, any vector that's perpendicular to V is going to be in the null space. Right. So what does that mean? That means that W is perpendicular to all vectors in the null space, and V is also perpendicular to all vectors in the null space. They're both perpendicular to all vectors in the null space. But what's the dimension of the null space? The dimension of the null space is n minus 1. There's only one dimension left. That means V and W must be in the same direction. All right. So V must be a multiple of W. Okay. And that's going to give us that's also going to give us symmetry. Now we could actually have just used the symmetric matrix directly to show that W equals CV, and that's talked about in one of the problems below. So I think those are all right. So one more projection or two more projection problems. Okay. All right. Number 9, show that if P is an orthogonal projection, then M equals minus P plus I minus P is an orthogonal matrix. Okay. So you can just go ahead and write that that M is an orthogonal matrix by the orthogonal relation is that M transpose M is the identity. Just plug this form of M into this equation, M transpose M, and work it out that you get the identity. Of course, you'll have to use the symmetry of P, that P transpose equals P. Okay. All right. All right, number 10. Supposing that M is n by n and the rank of P is R, what are the eigenvalues of M? Okay. Is M a rotation or a reflection? Rotation means the determinant is 1. Reflection means the determinant is minus 1. All right, well, let's consider the relationship between the eigenvectors of M and the eigenvectors of P. Now, P has two different types of eigenvectors. So you can say if Px is equal to x, that's one type. See what that means for M. That's going to be true if and only if Px equals x, you can work this out, that Mx is equal to, let's see how that works out. Px equals x means this becomes x, I get an I minus x, and then here I get a minus x. So it looks like Mx is going to be equal to minus x. Okay. And then Px, the other case is that Px equals 0x. Okay, so that's the other type of eigenvector. That's going to be true if and only if what? Well, if Px equals 0, then I just have the identity left here. So that means that Mx equals x. So that means that the eigenvectors of P with eigenvalue 1 are eigenvectors of M with eigenvalue minus 1. And the eigenvectors of P with eigenvalue 0 are eigenvectors of M with eigenvalue 1. So let's just write that out. Of P with eigenvalue 1 are exactly equal to eigenvectors of M with eigenvalue minus 1. Okay, let's see if I can fix this. Does it know that word? Yes, it does. Okay, does it know this word? Yes. And then we also have the same statement, but this time we have it with eigenvalues of p with eigenvalue 0 are exactly the eigenvectors of m with eigenvalue 1. So we have the 0 and 1 mapping to 1 and minus 1 respectively. All right. So if the rank of p is r, that means I would have r eigenvectors with eigenvalue 1. And that means there's r minus 1s. Right? So whether m is a determinant or not, is a reflection or not, depends on the determinant of m. And you can think if there are r minus 1s, then the determinant is minus 1 to the r. Okay, so if r is even, then the determinant is 1. If r is odd, the determinant is 0, is minus 1. So that will determine whether the m is a rotation or reflection. Okay. So if you saw in the book, when r was equal to 1, you got a reflection. It's called a householder reflection. But you can have r being any number, which will give rotations or reflections. Okay, so I'm going to stop the video here. I'll make another video for the next series of problems.